very kind with me and patient. I'm a professor at the parasitology department and the Institute of Biomedical Science at the University of São Paulo, and just dialoguing a little bit with Camilo, who just presented. I'm an electrical engineer, then I did a master's in math, then I did a PhD in parasitology, a postdoc in public health. So I'm still finding my way, but somehow I ended up on the parasitology department. And at some point on my postdoc, we were seeing some results from mathematical modeling infectious disease that could be applied for some networks, and let's see. So I wish Thiago were here to help me explaining some of the details, but he's not here. So I was working together with Antonio and also Gabriela Gomes by the time, and then we saw the things, but we didn't know how to tell the history and how to unpack the theory behind all this. And then we went to Thiago, and he helped us. Thiago and Zeng, he is his PhD student. So please be kind. So starting with this compartmental model in epidemiology, everybody knows this. You have a susceptible population, can be exposed to some pathogen, and then we become infected and can recover according to some rates. This is very simple, and one assumption of this model is that populations is homogeneous. Okay, I'll try to be more kind. So if you are susceptible to a pathogen, you can get infected if being in contact with someone else or with the pathogen in some different places, and then you can follow these dynamics. This was discussed during the pandemic a lot of times. So, but the assumption of this model is that population is homogeneous and everybody has the same chance to get infected. We went, so then you have here the dynamical systems, and then of course everybody starts, if it's a new pathogen, everybody starts susceptible, and then people get infected, and then exposed, then infected, and then recover. By the end of the time, by the end of this cycle, for example, you will have some dynamics like this. What we did, we just integrated here one X, and the X here means one trait that varies among individuals. This means that we are dealing now with heterogeneous populations. And all the rest is exactly the same. You have susceptible, exposed, infected, and recovered. And then by doing this, we have the system. This is an infinite size system. For each X, you have one system like this. And if you consider that R is in the real and positive, and X actually is given by a density, you have this heterogeneous population. You can start with a initial condition like this, and you can consider the coefficient of variation of this trait as it's written here. So if you have this system, infinite size system, we end up having one very good approximation for this, and this is not infinite size, this is finite size, and then you can see the dynamics of the infectious disease for heterogeneous populations, just according to the coefficient of variation of your, in this case, a gamma distribution. And then this is much more easy to deal and to simulate everything. With this formula, we can calculate a very neat expression for the herd immunity threshold, in this case, and then this is according to R naught, and the coefficient of variation of this gamma distribution that represents the heterogeneity of the population. Here we are considering that the trait, it's connectivity levels, and this is the link with the networks. So one person can be connected with just another one or with many, and so then you have a graph. So then we did this, we obtained this expression, and then I was reading random works, and then I read one work from Tiago, and then I said, okay, why not try to apply something like this on networks, and especially considering heterogeneous graphs. What we did, so we have G as an indirect network on n nodes. A is the agency matrix, alpha is the complete strength, and C is the network mean degree. So this is the model we considered. This is a model that was used by Tiago and yeah, I think 2 or 3 papers of him, and then here we have a function that is like a doubling function, mode 1, so it's chaotic dynamics. And then we have the coupling strength. We normalize this by the network mean degree. And we consider then the network here, all the adjacent metrics and degrees. It's all integrated there. I think the model for you guys is much more clear than for me. So considering that it is, first, we did one, first of all, how we did this heterogeneous network. So just one example here, we consider 100,000 nodes, and then the degree distribution for this network, we randomly sampled from one inverse gamma distribution. It's here with mean 1,000. So the mean degree is 1,000, and the power law exponent was 3. And then after randomly sampling this inverse gamma, we have that we use a Bernoulli distribution, and the probabilities of 2 nodes are connected were like the probability from one times the probability from the other divided by the sum of all the probabilities. Okay, so this was how we created the network, and then we simulated. When we simulated, we started the states with randomly sampled states, all of them, and then we obtained this. Yeah. This, when we saw this, was very interesting, but we didn't understand much what was that. At least beautiful, let's say. So here you have the degree of the maps. Here is normalized by the mean degree, and EU states of the maps. Here the normalization is different than the formula I put there. There I put mode 1, here is mode 2 pi, but anyway, it's the same. So you started with uniformly distributed states with different connections, and then you just simulate. And suddenly, something starts to happen here, and then here, and then it moves down. And then suddenly you have synchronization, or this that we are calling partial synchronization. Yeah? So it's not everybody synchronized, but there is one pattern here, yeah? It seems that synchronization starts with highly connected nodes and moves slowly to less connected nodes as the simulation goes on. So basically, this is what we studied. Another thing that was kind of interesting for us, the synchronized cluster is synchronized among themselves, but they do not have the same state. They move from state to state, but they are synchronized with their own peers. And then if we define this order parameter like this, And here we would have like the mean phase and the order parameter. We can see here that the mean phase is actually chaotic. It's not synchronizing to one specific value. And then if we just subtract the mean phase here, we can see this contraction here. So here you have here's normalized from minus half to half. And then you can see that here we have chaotic, and then everything concentrates around the mean phase. But the mean phase is chaotic. So it's a chaotic synchronization, something like that. Yeah. So then, so we posed this statement. There is a sustained cluster S theta synchronizing to the global field phase theta at coupling alpha, while the other nodes spread uniformly, more or less. Let's go back there. This is more or less uniformly. This is more or less uniformly. We just have synchronization there in the middle. So let's go back. So we assume then that if you are in theta, or in S theta, sorry, your phase is theta. If you are out of S theta, your phase is random. Then we posed this question: which nodes belongs to the synchronized cluster? So then we defined the local field for each node, P that belongs to S theta as this, and then we can just multiply these both sides for this factor here, and then we obtain again the dynamics of the network according to this parameter. Yeah, but so after doing that, we can just define one new variable that is just how do you say this? Rescaling, or yeah, just to have the mean field as 0 for S, and then we can rewrite this. So we can just parameterize again this function as this. If we derive, and we can see that, so if we derive around S0, and S0 is a fixed point here for this equation, this is going to be stable just for values of beta, or values of this that is less than 1. Then we can just obtain that beta, or the fixed point S0 attracts when beta is between this range. If it's between this range, we can just change here again, and we know that nodes that here is the mean degree, here is the order parameter, alpha is the coupling strength. We know that in the asymptotic behavior, nodes in between these two ranges will synchronize. So we know in advance what's gonna be synchronized or not, just by knowing the structure of the network. So then so that was one work. Then we keep moving, and I'm not gonna have time to go in details for this one, but then we were interested to know, okay, so to understand what was happening here with the highly connected nodes. Then here we can just plot the order parameter for different values of connectivity. And then the order parameter, we can see that increase for highly connected nodes at the beginning, and then they decrease over time. And then just these middle connected nodes will become synchronized. So from here, we can more or less infer that this heterogeneous network, highly connected nodes are the ones that spark the synchronization, but after some time, they are not the ones driving the synchronization anymore. It would be something like if you have very popular people, if they send some information, then they change the opinion of the public, then they can do whatever they want. The opinion is there fixed, something like this. And just looking back here, at the beginning of synchronization, the order parameter is very low, right? Because we are not synchronized. If this is very low, this is very high, and this is very high. So only high connected nodes will synchronize at the beginning. This more or less gives the intuition of is behind here. Then the second paper, we showed that these dynamics for synchronization, the spark of synchronization, we studied the network before, give me just 2 or 3 more minutes, please. Before synchronization, which is not common, I think. And then we could see that the dynamics of the network before synchronization, it's well explained by this Markov chain here. Basically, you just start at 0, and then you have one parameter k, and then you square this, and then you have one noise. Basically, you have one circle, and then you have your order parameter, and then you have one noise. And then you square, and then you reduce, have another noise, perhaps another noise, and then you are around here. But if you are lucky enough to have noise in the same direction, after some point, this is gonna explode. And this is gonna synchronize. And the mechanism for this synchronization is well described by this Markov chain. Really simple, really simple. We show it that this process, the process here is our Markov chain is really close to the values of synchronization in our simulations. Here, there is just 10% difference. And I just put here the papers, and thank you, everybody, and acknowledge Thiago, Antonio, Gabriela, and Zeng, who were part of this work. Thank you very much, and sorry for being very fast in this last part.
Thanks, Rodrigo, for this nice talk. We have time for a very quick question, if anyone wants to ask. Okay, so let's thank Rodrigo again.
Thank you.
Now we're going to have lunch.